All right, class, today we're going to do a video on segments and circles. And I know you may say, well, we already talked about chords and secants and tangents, but when we talked about them in relationship to the angles that they form inside the circle. Today we're going to be talking about the lengths of these segments. And we know segments have finite lengths, so they do have a number length, whereas lines don't have a length. So we're only talking about segments, not lines or rays. And so let's take a look at two types of segments, circle segments, and we know that these are two chords. And if we take a look at the relationship between the chords, well, here's a blue chord and here's a red chord. And some of you may be saying, oh, well, the chord lengths are equal. Well, that doesn't always hold up. If we were to take this length and AB and add it to BC, we're going to get this length. But if we take this length, BE, and add it to DB, we're not going to get the exact same length. So these chords are not the same length, and even as I move these around, very rarely am I going to get where the chords are the same length, okay? Except, of course, if they will go through the center, then they both be diameters. But there is a relationship that goes on between them. Let's change this from AB plus BC to AB times BC and see what happens when I take the pieces of the chords and multiply them together instead of adding them together. And what you can see is, that they end up being the same. So even though I take this piece, and actually let me change it to red so you know that this is talking about the red chord, as I multiply the pieces of the chord together, I get the same answer. So, and the pieces be the piece that they're broken up into. So that gives us a rule. The product of the segments of two intersecting chords are equal. Okay, and they are equal in this sense. So let's take a look at our notes on page 161. And here we have if two chords intersect in the interior of the circle, then the product of the lengths of the segments of one chord is equal to the product of the lengths of the segments of the other chord. And that's what's going on right here. So I can say that over here, EA breaks up into, chord AB breaks up into EA and EB. And therefore, then we have another chord, which is CD, and that breaks up into EC, and if you said ED, you're absolutely correct. So the products of the pieces of the chords are equal, not the lengths of the chords are equal. Now let's take a look at another type of intersecting line segments in circles. Now here we call these line segments secant segments because they don't begin and end on the circle. They may begin on the circle, but they end outside the circle, as we can see here. And in the interest of time, I won't have to show you this, but if I were to add up these two, I wouldn't get the exact same thing as these two. So the lengths of these segments are not going to be the same. But does the relationship still hold about their products? So let's see. Let's take the product but if I take, instead of taking the product of the pieces, I'm going to take the product of the entire secant AC and multiply it times the piece of the secant that's outside, the external side, and I get this product. And when I do the same thing for the red secant, I take the entire secant, which is EC, and I multiply it times the piece of the secant that's outside, which is CD or DC. I get the same product as when I did that with the blue chord, even though these segments are not the same length. And this holds no matter how long one is and how short the other is. The product of the entire secant times the external part is equal to the entire secant times the external part of the other secant chord. So that leads us to this theorem right here, theorem 10.15. And as you can see here, we are talking about the entire secant EB, and we can multiply that times, if you said EA, you were absolutely correct. So the entire secant, in this case they just switch it around. So this case is the external part times the entire part. And then over here, for the other one, we have EC, the external part, times the entire part, which we know to be ED. Okay? So it's important to remember it's for this theorem, it involves the entire secant times its external part. Okay? And though that product will be equal to the product of the entire secant of the other secant segment times its external part too. Okay? Let's take a look at another theorem, relationship between a secant and a tangent. So here we have a secant segment and we have a tangent segment. And what's the relationship between there? Well, as you can see, these segments are not the same length. That's obvious. But let's talk about here. Let's see what the relationship is between the entire segment, secant segment, and the external part. So when I do that, I'm going to measure that. I'm going to take the entire segment, which is BD, times the external part, which is BC, and compare that with, well, this is a tangent, so it doesn't have a part that's inside the circle. The external part is the same thing as the actual tangent segment, so we're going to just multiply them by itself. The entire tangent times the external part, which is in this case the same thing. And as you can see here, the products are the same, and that happens even as I change their lengths. It doesn't matter about the circle size or the lengths or the angles that they form. So here we have a rule that says the tangent part squared, the tangent segment squared is equal to the whole secant times the external part. So over here in our notes, we have the same situation here. Here's my tangent part. Okay. And then it's going to be equal, that tangent part squared is going to be equal to the product of the entire secant segment and its external segment. Okay, which means that should be in ED, the entire segment. Oops, let me change this from EC to ED, typo, times its external part. Let me change this to EC. I don't know where this came from. Okay, and that's that theorem. And that's the extent of what we're going to be working on next class. So happy studying.